So what I'd like to do today, because we have a lab that's going to require roughly 30 to 40 minutes of our time, is to work this second problem here from the in-class assignments, because I feel it's very representative of what might show up on your exams. And then once we finish that up, you guys will all split up and go to the labs and all that kind of stuff. Take care of your lab and stuff. All right, so with that in mind, Kendra, I did remember to actually share the screen, right?
Yes, sir, you did.
Cool deal. Alrighty, I should probably put everything up on the projector with everybody in the classroom so they can see what I'm doing too. That might be nice. And it's working, great, okay. So problem 2 asks us to calculate the maximum amount of power that can be delivered to a well-chosen load resistor RL. So our ultimate goal in this problem is to wind up with one of the two following circuits: a practical voltage source equivalent circuit connected to our resistor RL. So this is one potential outcome. We have some voltage Vs, some resistance Rs connected to our load resistor RL in series like that, so that we can determine the load voltage VL and or the current IL easily and calculate the power. Other option, this guy on the left is what's called a practical voltage source equivalent circuit. And our other option is a practical current source equivalent circuit, where we might have a current source IS in parallel with that same exact resistance RS connected in parallel to our load resistor RL, over which a voltage drop VL will occur and a current IL will flow through our load resistance. So once we reach either of these two forms, that's the stopping point, because then we can change between these two at will using these source transformation procedures that were discussed in the video lecture. So first thing I'd like for us to do is identify the different practical sources in this circuit. So who can tell me what they are? Alrighty, so there is a practical source here. I'll just do it like this. 27 microamp source and the 750 kilo ohm resistor form a practical current source. Are there any practical voltage sources in our circuit? Yeah, so the 15 volt voltage source and the 1.2 mega ohm resistor also form a practical source, in this case a practical voltage source. So I believe we're going to need to transform both of them at least once. So which one would you care to do first? The practical current source. Okay, the practical current source is fairly straightforward. So our current source, our independent current source is going to transform into an independent voltage source in series with a resistor that was in parallel with our current source, which is a 750 kilo ohm resistor. And then everything else in the circuit is going to look identical. So we're going to have our 3.5 mega ohm resistor, our 1.2 mega ohm resistor, our 15 volt source, and again these two guys in series form our practical voltage source, and this is in parallel with a 7 mega ohm resistor, and lastly in parallel with our load resistance RL. So I don't presently have a voltage magnitude labeled on my voltage source. Do any of you recall how we performed the voltage or the source transformation to get a practical voltage source from a practical current source? Sorry, what was that? Exactly right. So we multiply the currents times the resistance, just Ohm's law effectively. So we're going to have, if I can get out of this mode on my calculator. I don't know what I did with my TI calculator, so I'm left with this Casio that I barely know how to use. So somebody else do the math. Let's do it that way. I literally can't figure out how to get out of the equation solver on this dumb thing. Yeah, I finally got out of it. Thank you. So 27 times 10 to the minus 6 multiplied by 750 times 10 to the positive 3 gives us 81 over 4, which is 20.25 volts. Alrighty, so what did that source transformation do for us? Mega. Capital M is 10 to the 6, little m is 10 to the minus 3. It's a pretty important distinction because it's a billion times different. So just wanted to be clear there. But you're correct. Now the 750 ohm or 50 kilo ohm resistor is effectively in series with the 3.5 mega ohm resistor, so we can combine them into a single 4.25 mega ohm resistance. All right, so there's no other, like we can't do any more resistor combinations or anything like that right now. So what is the next thing that we should do? And I'm gonna move this guy back to the other resistor wall, and you'll see why in a second. What's next? Okay, so we transform the 15 volt and 1.2 mega ohm resistor into a practical current source. So that's going to put the 1.2 mega ohm resistor. So I want to be clear about what I'm doing here, actually. Okay, so this is where it was connected. Like so. So I'm literally plucking those two elements out, transforming them, and then putting them right back into the circuit, okay? So the resistance value stays the same, so that's 1.2 mega ohms. And our, let's see, we had a voltage, so we're going to have a current. The positive polarity terminal of the voltage was on top, so that means the current is going to be directed up. So the arrow, the head of the arrow should be wherever the positive polarity terminal was. And we're going to use Ohm's law again. So that's going to be 15 volts divided by 1.2 mega ohms. Gives us our current, which is 1 over 80,000, or let's see, 12.5. Let's divide this by 10 to the minus 6. Yeah, 12.5 microamps. My math is correct, and I believe it is. So the reason why I've drawn it like that in this particular way is to illustrate that we're literally just taking these elements out at these particular terminals and then putting them back in. Now, if we identified our nodes here, and we're not going to go through coloring things in and all that kind of stuff, but we can see that this node up here and this node right here are connected by a wire. So I could redraw this like so. And I can do the exact same thing on the bottom. And it may be more obvious now that that places the 1.2 mega ohm resistor in parallel with the 7 mega ohm resistor. Now we could do a combination here, but I'm not going to do that just yet, okay? And the reason why should be obvious in just a moment. But if we do one last source transformation on the practical voltage source on the left-hand side, where we have our 20.5 volt source and our 4.25 mega ohm resistor, if we transform these guys, oops, I didn't mean to delete that whole bottom thing. So this is 4.25 mega ohms. And we're going to have now a current source. Since our voltage source was direction up, or excuse me, positive polarity terminal on top, we'll have the arrow pointing up, 20.25 volts divided by 4.25 mega ohms gives me a not pretty number, 4.765 microamps. And hopefully it's pretty obvious to why I didn't do the resistor combination before. Now I see that I have 3 resistors in parallel, so I would have just had to do resistor combination twice instead of doing it once. So from the perspective of our load resistor, we have 2 current sources connected in parallel. So what does that mean we can do? Combine them. So it's going to be 4.765 plus, where's the delete key? The 12.5, since they're both in the same up direction, we can just add them together. Yes, ma'am. I'm sorry, I couldn't understand your question. Okay, so the voltage source, if the positive polarity terminal is on top, the head of the arrow should be pointing to where the positive polarity terminal was. So the arrow should go from negative to positive. So that's why this guy is directed in that way. Now before, when we did this transformation on this guy right here, the head of the arrow is on top, so that's where I put the positive polarity terminal. And then when I switched it back, it would maintain its same direction. Okay. So let's see, 12.5 plus 4.765 is 17.265 microamps. And my equivalent resistance is just 1 over 4.25 mega ohms plus 1 over 1.2 mega ohms plus 1 over 7 mega ohms, all that to the -1 power. And so I get here 0.825 mega ohms, or 825 kilo ohms, but we'll leave it as that, connected to our load resistance RL. So that's just using resistor combination and source combination techniques to get to there. So you are asked to determine the to determine the maximum amount of power that can be delivered to a well-chosen load resistor RL. So what's the maximum amount of power that can be delivered by the network to the left of that dashed line? Maximum power transfer occurs when the load resistance is equal to what? The source resistance here. So we're looking for the maximum, the power that occurs when RL is exactly equal to that value of 0.825 mega ohms. And we've derived an equation for it, or I've derived an equation for it that I believe was in the lecture notes. Did I do it for practical current sources or just practical voltage sources? Just practical voltage. All right, well then let's do it real quick for practical current sources. It won't take a whole heck of a lot of time. So let's see. This is IL. And this voltage here is VL. Let me get that arrow out of the way, right? PL max going to happen when we're going to multiply VL times IL in this circuit above, where, let's see, VL is going to be our source current, so I'm just going to write it as IS right now, times those two resistors in parallel, which is just, since they're equal, they're both RS. So RS over 2, so that gives me VL, right? And then IL is how much current is flowing through the load resistor. Well, since those two resistors are identical, exactly half of IS will flow through it, right? So the current's going to split evenly between RS and RL when RS and RL are equal. So that means that IL is IS times, sorry, that should be RS, not RL, is I 1/4 IS squared. Hold on, I think. Yeah, I've got an extra factor of RS in here that I'm, oh, it's not RS, it's 1/2 IS, that's why. So there's the mistake. IS multiplied by RS over 2 gives me a voltage, and I'm trying to find the current. The current splits evenly among the two. So it's 1/4 IS squared times our RS value, which we can put in our numbers. 17.265 microamps quantity squared times 0.825 mega ohms. 6.148 with some rounding error in there times 10 to the minus 5 watts. So somewhere around 61.5 microwatts. Yep, there we go. All righty. So this material, source transformation and the maximum power transfer theorem are the last bits of material that will be present on exam 1. So the material that we're going to cover on Wednesday, which is our first bit on Thevenin and Norton equivalent circuits, and then the material that we're going to cover on Friday, which I think is our, wait, is today Wednesday? Okay, sorry, what we're going to cover on Friday then is Thevenin and Norton equivalent circuits. And while you'll find that it actually can be used for your circuits one, or for the exam 1 material, it's not required to be known. Just to give you guys a heads up, this source transformation stuff that we did here is really valid, but there might be times where we can't simplify a circuit down to an electrically equivalent voltage source or an electrically equivalent practical current source just using source transformation techniques. Thevenin and Norton equivalent circuits give us an alternate route to get any circuit, any two-terminal network down to a practical voltage source or a practical current source. So it's a little bit more powerful, but this is pretty easy to work with. All right, it's 1:30, so let's go ahead and get things rolling. Today we have a lab that'll take roughly 30 to 40 minutes, I believe. So to that end, we're going to work this one problem. It's problem 2 from the in-class assignment because it's very representative of what might show up on your exam. And then after we finish that up, you guys will work on the lab. So the lecture material was all about what's called source transformation. Being able to convert a practical current source, which is a ideal current source in parallel with a resistor, into a practical voltage source, which is an ideal voltage source in series with a resistor, and that thing is restarting itself. I'll just keep talking for a moment. So you can convert practical current sources into practical voltage sources, and vice versa. So, work. I think this room is haunted in such a way as to make me not able to do what I need to do. All right, fine. All right, so in this circuit, there are 2 practical sources. Okay? So the first one is this practical current source. It contains an ideal current source in parallel with that 750 kilo ohm resistor. And our second practical source is this practical voltage source, which contains a 15 volt source in series with a 1.2 mega ohm resistor, excuse me. So our ultimate goal in this problem is to effectively simplify this circuit down using source combination and resistor combination source transformation and resistor combination techniques to get either a practical voltage source equivalent circuit where we have some voltage Vs in series with some voltage Rs, which is connected to our load resistor, RL, like so. Or alternatively, it's electrical equivalent, which is a practical current source representation. So we have a current source IS in parallel with the exact same resistance RS in parallel with our load resistor, like so. So these are our ultimate goals, either one or the other, because once we get to one, we can immediately transform it to the other. Okay, so this is all about source transformation. So how do we transform the practical current source on the left-hand side into a practical voltage source? Anybody watch the videos? Yeah, so simply multiply IS times RS. So that's going to give us a voltage source direction up, like so, where if IS was, well, it's going to give us 20.25 volts. I'll just jump ahead because I remember what it was. That's going to be in series with the 750 kilo ohm resistor now. That does not look like kilo ohm, that looks like gibberish. So I'm just drawing this set of terminals here real quick. Then we have a 3.5 mega ohm resistor. So before we get back into the circuit, I just want to try to make sure you guys understand what I'm doing. If I drew a pair of terminals right here on this original circuit, right, I'm effectively disconnecting the 27 microamp source in parallel with the 750 kilo ohm resistor, transforming it using source transformation techniques, and then reconnecting it to those exact same terminals, okay? And the rules are fairly simple. The resistor value has to stay the same, and we can use Ohm's law to get the voltage from the current or the current from the voltage. If the head of the arrow is at the top, then the positive polarity terminal is at the top. If the head of the arrow was on the bottom, positive polarity terminal, the voltage source would be on the bottom, etc. Now, we also have this practical voltage source here in the middle, which I've outlined in purple. And what we're going to do is convert it into a practical current source that we're going to connect to this set of terminals where that practical voltage source was. So first, how do I do that transformation? Yeah, Vs divided by the source voltage divided by the source resistance. So in this case, that's 15 volts divided by 1.2 mega ohms. So 15. I think it's 12 and a half, but I just want to double check. 15 over 1.2 times 10 to the 6. That's correct. So 27 milliamps is 27 times 10 to the minus 6 amperes. And I'm multiplying that by 750 kilo ohms, where 750 kilo ohms is 750 times 10 to the positive 3. So 27 times 10 to the minus 6 times 750 times 10 to the positive 3. Yeah, all right. All right, so back to our current 15 divided by 1.2 times 10 to the 6 is 1 over 80,000, which is 12 and a half microamps. So we're going to have 12.5 microamps here and 1.2 mega ohms here. So there's a couple of things that we can do here. The first, what benefit was transforming our practical current source into a practical voltage source? Let's start there. So going from this guy in orange to this guy in orange, how did that help us? Right, so 3.5 mega ohms is now directly in series with a 750 kilo ohm resistor, and so we can call that 4.25 mega ohms. All right, for him. Now, it may not be super obvious, but this 12.5 microamp source is now in parallel with a 7 mega ohm resistor, as is the 1.2 mega ohm. So this is something that maybe not all of you have noticed, but these two individual nodes are connected by a wire, which means they're all the same node. So I could easily extend this guy up like so, and extend this guy up and get rid of that and do the exact same thing on the bottom. Not required, just might make the circuit analysis look a little more normal, okay? So I can see that my 1.2 mega ohm resistor and my 7 mega ohm resistor are in parallel. So I could combine them now, but I'm not going to. And the reason for that is that if we look, we could see that another source transformation on our leftmost practical source would give us a single node pair circuit where everything is in parallel. Everybody okay with that? So if we divide 20.25 volts by 4.25 mega ohms, we get a current source direction up That is, let's see, 20.25 divided by 4.25 times 10 to the 6, 4.765 microamperes. And now we're at a point where, since everything is in parallel, what can we do with those two current sources? Right, they're both in the same direction, so we can add them together. So an electrically equivalent current source would be 12.5 plus 4.765 is 17.625 microamps. And now hopefully everybody can see that all three of those resistors are in parallel. So I can combine them all as well. So that's going to be 1 over 4.25 mega ohms plus 1 over 1.2 mega ohms plus 1 over 7 mega ohms. All of that raised to the -1 power, so we're taking the reciprocal. And we get 0.825 mega ohms connected to our resistance RL. So it's now in the practical current source formulation that we talked about at the very top of class. Okay. So we want to find the maximum power that's absorbed by this guy. Yeah, so RL doesn't have a value yet. Maximum power transfer occurs when the load resistance RL is exactly equal to the source resistance RS. Doesn't matter if it's connected to a practical voltage source or a practical current source, that is true. So our maximum power, so if RL is equal to RS, let's define a couple of things here. This is VL and this is IL. P max will be equal to VL times IL. It's just the power, right? Voltage times current gives us power. Well, when these two guys are equal, the voltage drop, VL, is simply going to be the current, the source current, times the equivalent resistance, which in this case is just RS divided by 2, right? If I have two identical resistors in parallel, their equivalent resistance is simply half of the resistance of one of the resistors. So this is IS times RS divided by 2. And this whole thing right here is VL. For IL, we have current that's entering a network of two identical resistors. So what's going to happen? So what happens when current flows into a network of two resistors in parallel, and they're identical? How does it split? Yeah, it splits evenly. So half's going to go through one branch, half's going to go through the other. So we can see that IL should be simply IS over 2. And this simplifies to 1/4 IS squared times RS. So I don't think I derived the maximum power relationship for a practical current source. I think I did it for a practical voltage source in the lecture notes. So now you've seen how to do it with a practical current source. Or we could have just done one more source transformation to make this thing a practical voltage source and then use that other relationship. Either way is fine by me. Yeah. So if we plug in our numbers here, that's 1/4 times 17.625 times 10 to the -6 amps quantity squared times 0.825 mega ohms gives us approximately 61.5 microwatts. Okay, so this bit of material on source transformation and the maximum power transfer theory is the last material that will be covered on exam 1. Okay, So what we're covering on Friday, Thevenin and Norton equivalent circuits, you do not need to know that to be able to succeed at exam 1. That being said, it wouldn't hurt or anything like that. It's just more knowledge on circuit analysis. But you don't I'm not going to specifically ask you for what's called the Thevenin voltage, Thevenin Norton current, or Thevenin resistance, or anything like that. So this is the stopping point for studying for exam 1. I just want to be clear on that to everybody. Yes, sir. 8. Yeah, so it's literally a 1-to-1 ratio. There are 24 lectures, there are 24 web work assignments. Not a coincidence. Now, the web work assignments sometimes drift a little and may, so like for really important concepts, you might see 1 or 2 problems on that on a homework assignment later or something. But for the most part, it's a 1-to-1. The exam is Monday evening here in the IESB, but not necessarily here in this room. We do have rooms reserved. I don't remember where they are right now. I think they're big rooms upstairs. I'm not sure how the different sections and all that kind of stuff are getting split up just yet. I have a meeting with Dr. Harper about that literally immediately after we finish up here today. So I'll put that on Moodle and let you guys know as soon as possible where you're supposed to go and all that kind of stuff. If for whatever reason you have to quarantine, or because the night exam, anyway, if you have to quarantine or whatever like that, there will be an online test also available that will require the use of the Respondus lockdown browser, which means that you need a laptop with a webcam or a desktop or whatever with a webcam, so that it can record you taking your test, and supposedly the AI will tell us whether or not you were cheating. You know, whatever, robots. So there is that option available for students that need it. All right, I think that's enough out of me with regard to lecture material. So, pardon? That is a great question, and it depends entirely on whether or not I have the test finished before Monday starts. So what I mean by that is we're not going to cover any new lecture material, but I may be able to do a review session or something like that for those students who want to show up. But that is entirely dependent on me getting the test finished before Monday. Because if I don't get it finished on Monday, I'm going to use that class time to finish things up. I've started on the test, which is actually a pretty good place for me to be in, because usually I'm working on it pretty much just the weekend immediately before, but I have started on things. So I think we'll be able to do a review session, but I'll let you know closer to Monday whether or not I'll actually show up. And again, this review session is not remotely required for anybody that doesn't feel they need it. It's just a service that I would provide if I have the time to do so. I can't force you to show up to class on the day of the test because the night test takes the place of the class day. Apparently there's been an issue within the College of Engineering and Science where some professors were covering new material on the days of the night tests, and that's apparently not appropriate. I've never done it, but anyway, so just want to be clear, I'm not making you show up to class because I'm making you show up to the test.